Everybody stay tuned. In just a few minutes, we're going to have a panel of some of the speakers that you've heard already today. And I'm going to go ahead and bring our panelists on the screen. All right, welcome back, Pam, and welcome, Paula. So this first panel in the industry track is all about production AM for critical applications. So mission critical, flight critical parts, and things of that nature. Our panelists are a couple of people that you already know. So Pam Waterman from PADT, SJ Jones from Velo 3D, and we're bringing Paula Claras on. She's an AM engineer with Cumberland Additive. So just to kick things off, I'd like to have each of you just give a real quick introduction to who you are, where you work, and the ways that you're using 3D printing. So Pam, can we go ahead and start with you?
Sure. Hi, I'm Pam Waterman. I'm a 3D printing application engineer at PADT, Phoenix Analysis and Design Technologies, in Phoenix, Arizona, in the States. I work with current and prospective customers of Stratasys polymer 3D printers, helping them determine the correct match for their application so they're getting the right printer, they're getting the right build volume. They have a range of options of materials, helping them figure out the properties of those materials, using the software to set up parts for printing, discussing post-processing techniques, and just any of the big picture questions about how to make additive suit their application.
All right. Paula, let's go to you next.
Sure. Hi, everyone. My name is Paula Clares, and I'm an additive manufacturing engineer at Cumberland Additive. I am located in the outskirts of Austin, Texas. And prior to joining my role here, I completed my master's at Penn State in additive manufacturing and design. And in my role at Cumberland, I work with powder bed fusion technology, and I work with customers from a wide range of knowledge, either from customers that don't know anything about AM and are just entering to AM, to customers that have been using AM for a couple of years. And I assist with and manufactured and use parts for different industries. Some of the most popular I work with directly are aerospace, space, and energy.
Great. And then SJ, I know you just got off stage, but
Hi, everyone. For those of you that just joined, my name is SJ. I'm currently a technical sales engineer at Velo 3D, which essentially means that my role is to sit in the room and make sure sales doesn't promise things that we can't actually deliver. But before that, I worked at Siemens Energy, printing a lot of industrial heavy gas turbine stuff. And then before that, I worked at Aerojet Rocketdyne on a lot of their space applications. My primary focus is in powder bed fusion, and my favorite material is aluminum.
awesome. All right. So let's just get started with this conversation by putting some parameters around it, kind of identifying the types of parts that we're talking about. So what are some examples of flight or mission critical components that are being made additively today? And ideally, what are some that you personally have had experience with?
Yeah. So I actually brought some parts just to do a little show and tell. I know people like to see actual parts, but to answer just in a very broad, what type of parts are being additively, it can be a range. It can be from jigs and fixtures to prototypes to end use parts. But I would say, at least from what I've seen and the exposure I've had, I think for aerospace specifically, talking brackets are mostly what are getting printed out there. Like most of the companies in aerospace are printing some sort or some variation of a bracket. So I would think that's the most popular. And trying to compare how are these additively manufactured parts different from the traditionally manufactured ones, I would say that the major differentiator is when they incorporate the benefits for AM. So if that new part uses some sort of like lightweighting technique, or if it's using some complex geometry, if it's using part consolidation, or if it's having a shorter lead time. So these are just some benefits that we know about AM that these new parts might have. But that is not to say that all of the parts that are getting 3D printed out there use all of this or any of those benefits. So to explain how a 3D printed part could be just identical to a traditional one, I want to show this bracket. So this bracket was printed for the aerospace industry. So the customer is Airbus, and we printed it here at Cumberland Additive, and it's made of Ti-64, so titanium. And the only difference between this and the traditionally manufactured one is just the fact that it was 3D printed. Like the geometry is identical, the mechanical performance is the same. It pretty much is just a same part, but it was just 3D printed. The reason why they 3D printed is just to dual source. That's the only benefit they wanted. They didn't want anything different. So what's interesting about this part is that it's actually the first Ti-64 part that is installed in a component that it's qualified for a commercial aircraft. So that is like pretty huge for additive and for aerospace as a whole. But like I said, it's not incorporating any of those benefits of additive. So having seen this, we internally wanted to see, okay, what if it incorporated some of the benefits? Would it look that different? And then something like that. So let me just hold them like side by side so you can see. It did incorporate all those benefits. So like different geometry, lightweighting, topology optimization. So in this side, you are exploiting the talents of additive. You're designing the part for additive, and you're able to bring those benefits as opposed to this one. So that's just one example that I thought like would be nice to see. And then another one that also incorporates some of the benefits of additive manufacturing is for the space industry. So this one over here was printed also as well here at Cumberland for NASA for their Orion vent housing. And this is made of nickel 718. So initially the traditionally manufactured one that we see here was conformed of 6 parts that then they were like put together as an assembly. But in the additive manufacturing case, they use part consolidation. So we were able to print this all into one. So that's a major difference between like the additively manufactured one compared to the other one. And then with part consolidation, you do have a lot of benefits. For example, like you have, like the part has a higher structural integrity just because like you're not joining, kind of like SJ was saying in her last presentation, you're not joining all these parts and you don't have like this critical like joint fixtures that could have potential stress. So I think that's just, I mean, there's a bunch of other parts out there, but I think for the sake of like keeping confidential our projects and our customers, I just thought this would be a really good show and tell.
That's cool. I like the bracket example because we tend to think of like aerospace and space parts as being really cool and sexy, and like actually brackets are pretty cool and important. Pam, are there any examples that you would point to as being particularly interesting, maybe on the polymer side?
Well, one that came to my mind is part of the jigs and fixtures world, which, as Paula mentioned, is actually kind of like the unsung hero in some ways. You know, thousands and thousands and thousands have been used already. And one of the customers that I've known about is Boom Aerospace, that's working on the new hypersonic airplane. And they have this outstanding photo that shows thousands of fixtures that help them align the heat special tiles that go on the outside of the aircraft. And because of that unique curvature, every single one of it has to be bolted on with a fixture that's unique. So there are hundreds of these fixtures. They're 3D printed out of polymer. Each one has a slightly different shape, and it's got drill holes for working with composites and putting other additives, you know, onto the aircraft. And they are able to make each one of those individually and save incredible amounts of time as well as money because they aren't trying to machine each of those individually. They just 3D print what they need. So I think that's one of those amazing, even though it's like, you know, in the back room type of application. Another thing, just down to earth, talking about the time savings, a couple of things. I got to work with something I'm going to talk about again, which is a car rebuild project. And this was a polymer part actually built upside down. It's the cover for an antenna blade that comes through the top of a car. So not like critical in its end use, but the time savings was amazing, because to think of trying to come up with a fixture and a mold and whatever process you were going to use to make that part in the automotive world, you would have to be doing hundreds of thousands to make it worthwhile. And we were able to design it, print it, turn it around in a day, because we did just need one. So the numbers are very relevant on both ends to why 3D printing can be important.
Awesome. SJ, did you have any examples you wanted to share?
So the TSA likes to confiscate my examples, so I tend to ship them back to headquarters because they're shiny and very pointy, and then when it lights up on the X-ray, they're like walking over to my suitcase, and I'm like, no. But like I would just say that like our biggest bread and butter at Velo are like compressors and impellers, like the ones that I showed earlier, volutes, anything that fluid flows through. That's essentially like where we really shine. And I've seen so many like oil and gas customers especially come to us because we can print at really low angles without having to put any material inside. And they come to us because they're like welding and brazing the top of the shroud on top of the impeller. So like if you imagine the impellers I had, imagine like a little hat on top of it. Well, oftentimes they have to like weld or braze that little hat on, and sometimes it fails, and then that creates scrap and it loses time. And so it's just a lot easier, they found, to like come through and 3D print it. And so like that's just been hugely dominating most of my workspace for the last 6 months.
Very cool. So what is one of the biggest challenges? I'll ask each of you this. What is one of the biggest challenges in working with additive for critical applications? So I guess we'll start over at the beginning with Paula.
Yeah. So I think that there are a bunch of challenges out there depending on what specific parts or like what industry you're working with. But I think if I could just, I guess, like generalize and put it like in a couple of points that I think are like the most challenging, I think the biggest one would be the lack of material allowables that is available when compared to traditionally manufactured materials. So we all know additive is not that new when you think about it. Like it's been around for a couple of years, but when you compare it to the amount of data that is out there for traditionally made materials, it's not comparable, right? So I do think that we're still not at this stage that we have all this data on how the material and the mechanical performance will behave, that it's still, I guess, I wouldn't say it's a challenge because people are still getting parts made, but it's still something that we need to overcome as a whole. The second one, talking about material, is the materials available. So again, same thing. There are a bunch of materials that can be additively manufactured and that are great and that they have a lot of benefits, but there's still not that many when you put it in perspective to all the materials out there that are used for different industries, aerospace, space. And even the materials that we are working with in additive don't have that better performance when talking about fatigue life, which is like super critical in this application. So we always tend to either underperform or just sufficiently perform in something like fatigue life. So that's something that still needs to be, I guess, like figured out as a whole. And then the third one, I would say size limitation. So kind of tying to SJ's presentation, I think like the biggest part that can be printed nowadays commercially available is tied to the build envelope of the printers. I do see a lot of opportunity moving forward in just having bigger printers with more lasers and more capability to just be able to produce these big parts that are needed for critical applications.
So let's jump right to SJ then. Do you have any any response or other challenges you would point out?
I would say that the biggest challenge from my perspective with AM that I used to have with like a lot of customers that I try to incorporate with my current customers is a lot of customers don't think last step backwards. So when you work in like additive applications, you think last step backwards. So the last step normally is quality, and that step normally involves like, how am I going to inspect this part to verify that it is what it is, that it's all the way solid, that it's all the way done, so it's going to perform the way I need it to. What tests am I going to run? And then you kind of have to like walk backwards from that. So like I have customers that will like design these like super thin walls, and then they'll get to the end and they'll be like, so is it good? And I'm like, my job is to print it. My job is not to tell you or assess whether it's good. Did it print the way it was supposed to? Yes, that is my answer. So how are you going to inspect it? And then the customer's like, well, I don't know. Well, how about we just CT it? And I'm like, well, what if it's too thick to scan into? So like a lot of customers are getting bitten because they jump the gun. They don't think about how they're going to assess the quality of the part after it's printed. In terms of inspection. So like you should always plan your inspection method. Don't design a part that you can't inspect. This was a very big common talk at ICAM with Aerojet, where they had talked about how they had printed these volutes and they couldn't use them, even though they knew the print was sound, because they couldn't inspect it and then prove it through the inspection method that the volute was sound on the inside. So we're coming up with a lot more creative like inspection methods that I've been hearing about through the pipeline, and I'm excited for some of those to hit. But until then, like one of the biggest challenges I think that we have right now is like better inspection methods for like all of these crazy tight small geometries inside of these large metal frames.
Oh, that's such a good point. You can't trust the part. You can't use the part if you can't inspect it and verify that.
Mm-hmm.
Pam, what would you say as far as the biggest challenges for these types of applications?
I'm finding customers are still saying, okay, those are really cool parts. I like how they're performing, but I need to manufacture these at large scale. How are you going to scale that up, and how are you going to fit that into a traditional manufacturing workflow? These cannot be standalone machines anymore if they're going to be a viable part. How are you going to track the data that goes in? How are you going to confirm that what you are signing up to print is what's going to be printed? How do you handle IP? How do you handle the number of trading off? How many pieces of post-processing equipment do you need per printer? You know, do you need extra? Can one handle the output of 3 printers or vice versa? So looking ahead, bigger picture, as well as the physical plant that has to support it. Those are all big questions that have to be addressed. And they're different for each of the technologies. It's different for polymer versus the metals and on down the line. Working with ceramics is going to be different too. I think it's fascinating. We're getting more answers, but those have to be asked.
Can I add on to that?
Mm-hmm.
Yeah.
So like one of the big things that we like to really advertise with Velo is scalability. So we have really great scalability because of the golden print file, and that essentially starts with like good CAD going in, not an STL, and getting good print files out. And then because of like all the quality checks that we run before the machine, like it just consistently prints the same part. And we've tested this across our entire fleet, but we do have like this thing called the CM network that allows our customers to scale up and scale down. And it also allows our CM partners to scale up and scale down as well. So like if we're seeing like a huge demand in the market, normally like our sales team is going to know that that demand is coming. So then we can like signal it up the chain and be like, hey, we've got lots of demand coming. We might want to start placing more machines out in the field. Who are the ideal partners and like locations for that? And then like we'll scale those partners up and then scale them back down as needed. So like we've seen that that's been like really effective considering like how repeatable the process is. But yeah, that's just one of the things that I really wanted to highlight, because I think it's amazing that like we're able to do that and that we're able to offer that, because not everyone is able to like sit down and explain to their boss that they need to invest in this like multi-million-dollar like factory to make these parts.
So sort of speaking of that and the issue of adoption and trying to, get your customers on board with the right types of things that they should be printing, what is the learning curve that you notice with customers? Is it big? Is it decreasing? What are the things that they understand already, and what are the things you have to teach them?
Ooh.
Good question.
I'll go first if you want, Paula.
Yeah, go ahead.
So I would say that the learning curve, So like there's a misconception that when you come to Velo, like you can print anything. We can print almost everything. And then the whole support free thing, don't even get us started on that. Most things support free, but when you're allowed to print with really low angles, it opens up this door to like what I call DFAM 2.0, which is like we have regular DFAM and we print regular DFAMmed parts from legacy systems beautifully, really well. But then when you want to push that boundary further and you want to start thinking like, what could I do if I didn't have to adhere to 45 degrees? There's a whole new world that opens up for you that is really hard to wrap your head around if you've already come from a background in like legacy additive. So when like I have legacy AM people from like traditional AM come over and they're like, yeah, well, do you have to put support here? I'm like, no. And like, well, how do you know when you put support somewhere and when you don't have to put support somewhere? And I'm like, well, let me introduce you to like this whole like DFAM 2.0 concept. And so like explaining that to them and like seeing that, oh, you really start by having to teach them literally just the foundations of like the physics of laser powder bed fusion and like how like our system isn't adhered to like the recoder hitting. And then once they get those two things together and they start seeing the geometries, the light bulb starts going off and it's great. But I do think that it takes a bit more training to get to that advanced thing. Like you can't just hop in the Ferrari and start whipping around doing donuts.
I'll jump in on the polymer world because it has a lot of similarities and then differences. I think the number one challenge I find with the new customers and learning is understanding the wide variety of materials that are out there, how they are similar to what's in the traditional world, like working with ABS, or how they could be different, how they could be even better. Have there been additives, kind of no pun intended, in a filament or in a resin, depending on you're talking about a filament printer or a DL printer, and what are your end uses? It always comes back to what's the end application. Are there temperature requirements? Are there chemical operating requirements? What's the environment it's going to be in? Not just strength, not just elasticity kind of thing, lifetime. Are you going to have to be able to sand it or drill it or paint it? And that also can align with standards that are being developed out there more right now in the metals world, but I think it's going to be coming to the polymer and the resin. The medical world, we have applications that have to require biocompatibility. Can a part be sterilized? The things that the people need to bring to the table, it's definitely a partnering. And that's one of the reasons I find it fascinating, because every application is different. But if there are standards they can fall back on and educate us, we can help them do a better job of matching. And then it's always just exciting to see the research that's being done too. So I think people need to be aware that just if it's not available today, it might be next year.
Mm-hmm. Yeah, I think Pam pretty much touched on almost everything that I think and I encountered. In my role, I work, like I said at the beginning, with a lot of customers that have already entered additive in some form or are already knowledgeable at some form, but I also deal with customers that have never done it. And it's the very first time. So I think it's just kind of like that mind blown of like, what is all of this? Like, I just don't know anything. I don't know the first thing talking about design, like what are some design changes I can make, design iterations. Some of them really like to be involved in the process, to be like, okay, like would this be better than this? And like, can I do like internal channels, and can I just do like very complex stuff? So that's like a topic that I see a lot, just kind of like being very like hand in hand with this learning curve, like just like doing the design iteration and adjusting their part for additive. The second one, and I would think the biggest one, is materials and heat treatments. So not only what material can I use, but what if I use this material and I were to use this heat treatment? Would that be better for my application, worse for my application? How would that compare to mechanical performance of a casted part or of a forged part? So just that whole world of heat treatments paired with a material and mechanical performance. So yeah, I think we see a lot of questions there. And then again, touching on a point that Pam already talked about is the standards. So there are a lot of new standards specific for additive that are being developed or are in the process of being developed right now. So we see a lot of customers that have questions about this. They want to know, when are they applicable? Can they stick to traditional material standards? Are they still holding like that qualification when you're dealing with AM. So that whole talk about like they want that guidance and they want to understand, but they also want to keep in perspective always how does it compare to traditional? Always like, okay, I'm doing all of this, but how does it compare to that? So yeah, I think just to answer, I guess, with a yes or no, I think there is a learning curve. And I would say like most rather than like most of our customers are more excited to jump in that curve and just like try to learn and absorb as much as we're willing to work with them, as opposed to just being like, oh, this is too much. Like this is a whole different world. So it's definitely encouraging to see that people really receive all of this and to see them all excited. I was at that point, like when I just started in additive, that I was seeing like heat treatment and design and all these possibilities. And I was just like, this is too much, but I love it. So it's good to see that on the other side.
All right, so let's talk a little bit about workflow. Like as you think about getting into like serial production, as you think about scaling up into repeatable part production, what are the workflow elements that a manufacturer needs to establish and manage to ensure that they're getting consistent quality parts every time? Pam, do you want to lead us off?
Sure. Again, mostly from the polymer world, but I understand this is absolutely true in the middle too, is starting with tracking your material. If you're going to be making critical parts, you have to start at the very beginning so that you know where the source of the raw material is from. Tracking the lot, the build date, the manufacturing date, as well as where it came from, and then how that raw material was processed into the form that you're going to be using, whether it's going to be a powder, like we use powdered nylon in some of our printers. We also have the filaments and we have the resins. So, and as the part is made, you can be able to go back and track exactly what it was made from, in case there is any kind of question. And for the aerospace and space applications, it's absolutely going to be critical, again, with the medical, probably also with the automotive, more and more. It just makes sense that you track that kind of information. Secondly, I would say it's locking in the build file, because there are so many different ways to produce this. As SJ said, STL is not going to last forever. We happen to work a lot with 3MF files because we do full color printing. You add that in, but there's security that gets involved with this too, and I think we might talk on that also. But you want to lock in the build parameters so that somebody else doesn't orient the part in a different direction, or trying to change the support material, or change if there's a scaling factor to it. You want it to be repeatable, the exact same part is being printed each time. I'll turn it over to the others because I know there's a bunch of other things.
Yeah. So for me, I kind of like think that there's just so many variables that come into play when having a part. So like Pam is saying, like just talking about powder, there's powder chemistry, powder law, powder manufacturing, like, and then talking about the machine, you have all the parameters of the machine and the files. So there's just so many variables that come into play for having a part from beginning to end, that I think that in order to be able to like have a managed and well tracked, it's like the industry is gonna have to move to developing more, again with the standards, developing more and more standards to kind of like determine what are the stuff that can be tracked and should be locked in, and what are other stuff that may be variable or that they might change. So for example, I just happen to really like the ASTM 52941 standard. So it's for powder bed fusion and it's for aerospace and it's for system performance and reliability. So it gives you a list of some of the stuff that you should be checking regularly just to make sure that you have a smooth workflow. That is not to say you cannot check other stuff, but it's just if you're sticking to a standard and you're following like whatever it's recommended, at least you're giving a little bit more order, because I just think it's really hard to track every single thing that comes into play with having a build file. So yeah, I would say maybe I see an opportunity for the industry as a whole to start developing more and more like structure into what are the best stuff to track. Because like I said, there's just so many like categories and subcategories that can be tracked and should be tracked and should be controlled. So it's just a lot to try to do like for each and every single one of the builds.
So y'all gather around because I'm gonna give you like my hot take, my hot goss, like what I see that people just tend to ignore. So for me, like with production and critical AM applications, my greatest fear with that is that we don't spend enough time, to Paula's point, looking at the quality systems. Because when you start tracking all of these things and adhering to all of these aerospace standards, like every aerospace company has a different standard that they want you to hold to. And then you have to come up with this like fancy quality system to track all of it and maintain all of it. And that quality like system can be expensive. So for like smaller to medium sized businesses that are kind of like getting into additive, especially with like a lot of the at home manufacturing that we're seeing pushed for, I worry that they're going to price themselves out because of all the quality requirements that are going to be put in place. So there definitely needs to be a lot more thought into creating like these structures. So I've seen, for example, like service bureaus adhere to AS 9100 quality standards. And that's an aerospace quality standard, which is great and all, but it's very strict, very regimented. It takes a lot of labor to maintain it and keep up with it and track everything through it. Maybe you have a customer that comes to you for like a little rinky dink prototype that's going to cost maybe $10,000. They don't really care about all the aerospace stuff, but because your system is set up that you have to track it and put all this labor into it, it may not be cost advantageous because you have to raise your prices to maintain that quality. So just like understanding, like as Paula said, like what you need to track, what's important, and really focusing on that, rather than trying to do everything at once, I think is going to be critical, like as we go forward, and not just getting carried away with like tracking everything. Because I'd love to like talk to people who work in investment casting and whatnot. Like, what do you track? How often do you track your powder? What are your powder lot sizes? They probably look at me like I was crazy. Like, we don't do all that. It's not that crazy. It's not that serious. So we put a lot of pressure, I feel, on ourselves on additive because it's so new to like go this extra mile and because we now have access to track all these things. And I think we're just getting lost in the sauce. So that's my hot take on that.
Yeah, I think like going a little bit on what you're saying, like just because there is like just because it's easy to track all this stuff, like a bunch of these sensors, a bunch of these printers have like complex sensors that give you like data information about like all your build, the flow of the argon inside the printer, the temperature from beginning to end, the laser power. Like just because it's out there and it's easy to collect doesn't mean that we should spend our time just trying to figure out and collecting and tracking and all of this stuff. So yeah, we're like just pretty much like to sum up all of this and based on like everyone's point, like I think we still need to figure out as a whole like what are the best things to track depending on our application and on the parts that we're trying to achieve.
So we have kind of a related question that came in through the Q&A. And so how do you track the origins of materials that might be topped up, such as lot numbers for resins that are being added to a resin vat with existing resin? But I think this also would apply to like metal powders where you might be mixing the batches and that sort of thing. Um, can anyone speak to that? How you're tracking material that's not being, fully used in one build?
I can say with the resin with the DLP, we do set aside resin that has been used in a tray, and we keep track of it. We'll filter it. We might filter it twice. We'll do visual inspection. But if we have a mission critical part, we'll make sure that we're using fresh resin. Now, that's a lot more affordable with a DLP than with an SLA system, of course. I don't work with that as much. I think that you would, at a minimum, have to record that so that if a question came up, you would know that it wasn't 100% new. In the powder bed that we do with nylon printing, we are able to reuse 70%. And again, there are standards that currently are more of a visual of deciding that that's still a fresh enough powder. Uh, I think that we're going to have to develop systems based just on use data. It's one of those things that somebody's probably going to do a number of research tracking projects on. It's a little easier in the filament world because you just have a date on a spool. You use it once and then that's it.
My greatest advice to this question that I have run into working at like users of the machines is buy as much as you can hold wall to wall in the biggest container you can get it at once. That way you have a massive amount of material that's all the same, all from the same place, so that when you do have to top it up, it's all from the same big, gigantic bucket. It will save you a lot of headaches in the long run. By the time we were running full scale production, like, I mean, our machine was running round the clock nonstop. We were literally ordering it in 2-ton lots, and we were asking for bigger. We were like, we need more. We are renting out the facility next door. We're going to empty it. We're going to fill it with powder. Like, we want the biggest amount of powder that you can get us, just because it helps maintain our quality and eases us on like our quality tracking systems. Number one, buy as much as you can at once from the same lot. Material testing, all of that, like DFARS compliance, all of that, make sure you have that in order. And then you have to decide as a company, like through your own internal testing or through your own MRL or quality system, what you consider as like good powder and how many recycles you're allowed to have for like each powder. But yeah, that's my advice. Buy it big. Don't hesitate. don't have any reservations. You're gonna use it all. Just buy a lot. It seems like a lot in the beginning, it's not.
Yeah, I agree. And I think like for me, just on what I've encountered, yeah, it's not a bad thing to mix powder. So virgin versus like reused powder, it's as long as you are tracking it. But like Pam was saying, for most of these critical applications, you're gonna want to use virgin powder since the beginning. So as Jay is saying, just go big, buy all this powder. And if it's the case that you are still using virgin powder, I think it's also a good practice to just every once in a while, or if not per every build, depending on what's your qualification process, to look at the concentration, the chemical composition of the powder. Let's just say for titanium, you want to be tracking, is there oxygen pickup in that powder? So it's not a bad practice to keep track and keep this test just depending on what qualification you're following. But yeah, I would say that talking about critical application, although it's possible to combine virgin and reuse powder, it would we would try to just use that virgin powder.
Yeah, to add on to what Paula said, I like to call it unused powder because, like, I don't know, the word virgin has some, it's just weird for me. But like unused powder, we had difficulties with fresh unused powder spreading across the build plate because of the uniformity of the spheres or whatever. So we tended to mix in a little bit of like one recycled used powder, or we would run like a light zap over the top of the virgin and then push it back into the dispenser and then run it that way to get better spreadability across the plate. So like all this unused, fresh, never before laced powder doesn't always have like the ease of use that like people are thinking.
That's interesting. Okay, so we'll jump from materials into machines. So machine to machine repeatability has been a challenge that's cited with additive manufacturing. How much of an obstacle is that right now for critical applications? And if it is a challenge, how do you overcome it?
Well, I can go first. Y'all wanna? So for me personally, I've always been Team Velo for this particular reason. We've got like 900 something sensors on that machine, and they're constantly checking everything. We're constantly checking the laser alignment and things like that to make sure everything is Gucci as it's printing. And then once it comes out, it gives you like a build report with a bunch of graphs, and it's like it'll mark if anything is an anomaly or what have you to tell you, hey, this was freaky on layer 647. You might want to check it out. It's probably nothing. And so like having all those quality checks before, after, and like during the build is super helpful in maintaining like repeatability from build to build. That, and like I really think a lot of the secret sauce is in like starting with the nominal CAD and not using STLs. Because I find that like when you use STLs, because they're not as explicitly defined, even though they're easier to manipulate and transfer, like I spent a lot of time repairing STLs, and then people export them at different resolutions, and that resolution can affect the slice and it can affect the print quality. And so it's really hard when with that process. But when you have the nominal CAD, it's just like that one file that just travels through the whole system. I think that also helps maintain like a lot of our tight tolerances and things like that.
Yeah. On our machines, we can either do the STL or the CAD. Definitely, I totally agree. If you can have the CAD, that's the best. Machine-to-machine variation, that's something that the user needs to do their homework on. I think machines are getting better at being repeatable. The number of sensors increasing, absolutely. And, I would say work with a machine which has published data on repeatability, test data. They've done thousands and thousands of coupons. They've measured, was it built, in the XY plane? Was it built in the ZX plane? What measurements were taken? How many? What's the variation in the results? Statistical analysis on that. An example in the FDM world where that's become prevalent is for our program called the Aircraft Interior Systems, the AIS program, and that was developed jointly with the National Avionics Group at, let's see, I better get that right, National Institute for Aviation Research and the National Center for Advanced Materials Performance and Camp out of Wichita State, and that's for plastic parts put on the inside of aircraft. You have to not only qualify your machine, you qualify that like the filament is being dried so it has no moisture in it. You're printing certain test coupons over and over and over with every build run, and then those are sent away and measured by an independent test lab. So the entire workflow is being tracked so that you know that that machine with this material, with this process, is going to create repeatable parts. And I think that kind of process is going to be duplicated and expanded across all of the different additive technologies.
Yeah, I agree. I think like going to the points you mentioned, Pam, I think that just because you are qualifying for critical applications for a critical part or something, you're qualifying maybe the machine, you're qualifying the part, the process, like all this stuff, all your variables that I was talking that could be changed and could be selected, so many different ones, they're pretty much locked in. So even then, even when everything is locked in and everything should behave normally, you still want to be doing these checks, either if it's adding a couple of tensile bars or, like I said, collecting some coupons for doing chemistry analysis. Like even then, once you have qualified a process, you still want to do the best practice of constantly monitoring and constantly tracking this stuff just to ensure that yes, there is variability, but it's not significant enough.
Yes. The significance of the variability, boldface, italicized, underline.
All right, we've got 4 or 5 minutes left in this panel, so I think this will be the last question. But let's take a look at additive manufacturing kind of in the broader manufacturing environment. And what are some of the tools that you use or that are available to make additive fit into kind of a larger manufacturing workflow where you might have, CNC machining or you might have other processes to work in as well?
So one of my favorite tools is Datums. I used to work literally right next to the machine shop. And my favorite thing is to like walk down there and be like, do you need a sacrificial lamb on the build plate to practice on before I bring this through the shop? And it's normally like, well, this is like a really complex, like 5-axis operation that you're asking for. So I prefer if you put like maybe like 3 sacrificial lambs on there. Or like a lot of people who have never machined additive parts, they do tend to ask me for samples. So like we'll print like just like 2 by 2 inch cube so they can get a feeling for like how the additive part is going to like cut as it's like being machined as compared to like a more conventional material, because they do, I feel weird saying like feel different to machinists when they're working with them. So just providing more insight and education like towards the machinist by giving them more samples and more pieces to practice on has been like my #1 go-to tool when I'm fitting myself into the overall like manufacturing landscape.
Well, I've got some thoughts on the software side of things. And when you're talking about trying to bring additive into a traditional manufacturing kind of environment, just order intake. How do you process this? What are the steps that are going to be needed? And there are fortunately a number of packages now that give you options for handling things like that. There's solutions from Materialize, from Link 3D, Octane, which used to be a division of 3D Systems, and then GrabCAD, which is part of Stratasys, they acknowledge that if your equipment can't work with all the others, it's not going to be anywhere near as useful. So you want a single point of entry. How does somebody request an order? How do they upload their file? You talk about the big files. How do you protect it? How do you make sure that maybe a certain department or group can only request certain materials because of the way their budget is allocated? And then how does it get assigned? So you want your machinery and your software to all be talking to each other. Another aspect of that with some of the higher end printers is that they have the MT Connect interfaces, so that if you want to make it a closed loop, so you are monitoring different parameters of the operation, or whether it's just downtime or predictive maintenance, all of these things which have been done with other types of traditional machinery are going to be allowable and incorporated with the additive machines at the same time.
Yeah, I agree. Like, I think for me, talking about like closing the loop, and like as Jay was saying, like not just leave everything until like it hits machining and then now what? Like it's more about communication. Like this is a process that is complex and that requires like closing all or tying all from beginning to end. So the more communication that can be, or that can be expressed like from beginning to end, either if it's with inspection, if it's with the machinist, if it's just with the design engineer, like the more involvement there is from beginning to end, just the smoother things are going to turn out. So yeah, I would say, if talking about tools, I would say it's more like communication tools, because I don't have that much intake of like software tools like Pam is saying, but they sound great.
All right. So we are right at the end of our time. Paula, Pam, SJ, thank you so much for being a part of this panel. I learned a lot, and I hope everyone listening in did as well. So thank you.
You're so welcome. It's cool.
Thank you for having me.